So as usual, let's start by concluding what we did last time. We finished the chapter on optimality conditions for equality constraint optimization, and we established first order optimality conditions and second order optimality conditions, which I want to summarize. And I want to say that I finished this part of the script finally, and it's in the pipeline and will be uploaded during this lecture or after the lecture by Dimitris. Right, Dimitris, you will upload it now, if you didn't find a big error. So what we want to look at, or what we looked at in chapter 11, so chapter 11, and also chapter 12, which we will do today, we will always look at this optimization problem which has equality constraints. And we derived first order optimality conditions that say if X star is a local minimizer and LICQ holds at this point, then there exists a multiplier that we call lambda star. And this multiplier is making the gradient of the Lagrangian 0. And actually it means that the gradient of f of X star is actually can be obtained as a superposition of the gradients of the constraints with a lambda star. And of course it will also hold that our point is feasible. So these are the first order necessary conditions for optimality that we derived, and it's particularly these two conditions which are making these things powerful, because we from now on look for pairs of X star and lambda star together that satisfy these conditions, and it will be a root finding problem, possibly a nonlinear one, but this way we can actually find candidate solutions for optimal points very quickly and algorithmically. We also established second order conditions, and in order to do that in a nice way, we actually started to decompose this Jacobian of our constraints into a null space and a range space. So actually we could write that the Jacobian of G of X star transpose is given as something U, and then an S plus, and then something which we called Y transpose. And Y is one part of a basis of the full space, which can be complemented with another part which we call Z, and this whole matrix here is orthonormal, so that actually the null space is spanned by the matrix Z because it's orthogonal to the matrix Y. So whenever you multiply this with something which is in the range space of Z, it will give 0, and so that's why we are in the tangent space then. So the second order conditions are most easily formulated by using the Z. So what we had under LICQ, if I just want you to remember, LICQ implies actually that the linearized feasible cone at some point is equal to the tangent cone at this point, which then is equal to the set of all Z times V, where V is element in the space of remaining degrees of freedom. So that is our complete characterization of the neighborhood of our feasible point by tangent cone of linearized feasible cone, or just the range space of the matrix Z. So all these things are the same. And so now the second order necessary and second order sufficient conditions, necessary and second order sufficient conditions that we did at the last time of last hour were actually stating that the second derivative of the Lagrangian, but the Lagrangian we need to first define to make sure that we still have it. This was our Lagrangian for the equality constraint case, and now the second order necessary conditions, they say that the Lagrangian Hessian at the optimal point, when you project it into the subspace spanned by Z, should be a positive semi-definite matrix. And the sufficient conditions would say if this is strictly holding, and if the first order necessary conditions hold, then it is a local minimizer. Okay, so these are the conditions that we should remember and where we will actually build on. And I should say there's a mini correction for the exercise sheet. When you have in 1C, you should prove that you have found a local minimum point. We are not 100% sure that this is the global minimum. At least you can try to prove it also, but not with the techniques that we have learned until now. So you can just prove that you have found a local minimum point. And you can use, of course, which conditions of these you can use to prove that something is a local minimum. Must be the sufficient conditions. I would like to in the summary, I would like to come back to the meaning of these Lagrange multipliers and some interesting observation that I just wanted you to share. There was this crucial trick. The first thing was this condition here. We had arrived at this point where we just said that the gradient, if we project it into the directions in which we can actually move, should be 0. Yeah, so this was something that was still intuitively, I think, very clear. You move, if you move along a direction which is feasible, then the gradient in this direction should not improve or decrease, because otherwise you could find a descent direction. Do you find that intuitive? I think, yeah. So this was intuitive, and now we say this is actually equivalent, yeah, with saying that there exists a lambda, so that nabla f of x star is equal to the gradient of x star times lambda. So that's not so intuitive, I think. And the trick here was that we said actually this gradient can be decomposed into two components. It would be this nabla f, I omit the argument, can be decomposed into a component which is in the y space and one component which is in the z space, and these are the orthonormal basis vectors. Yeah, so it's a collection of columns which are all orthonormal to each other. And of course, in order to get the factors, you could actually just use y transpose times nabla f here, and here z transpose times nabla f. That's basic decomposition of when we have orthogonal vectors, right? So we immediately remember this was equal to 0, so this whole part here vanishes, and then there must exist something, namely this thing here, which multiplied with y gives nabla f. Huh? So we can immediately see that this is equivalent, and we could immediately see to saying there exists something that we call u, which would be this quantity. Which creates the gradient. And now the trick was that we use this decomposition here, and that we basically put here in between. Yeah, so we have already this thing, df is equal to y, and then times y transpose nabla f. So this is something we know already. Yeah, so nabla f can be written as y transpose nabla f. That's equivalent to saying that this projection on the null space is 0. But now we see that this can be actually somehow rewritten if we do here an s plus transpose and a u transpose. This transpose we don't need, but here we can have a u, and then we have an s plus to the -1, and this transpose doesn't matter. So I didn't change anything, I just put a unit matrix here, and then this is also a unit matrix. So I didn't change anything. But what is nice now is that this thing is exactly the transpose of that thing, so I can actually now write it as nabla g of x star times u s plus to the -1 y transpose nabla f. And then we say this thing we just call lambda. So there exists some lambda that has this property. So what I wanted you to note is that the lambda, under all these conditions that we stated, can be found explicitly if you want. It's not something that we will do, but it's something that I would like you to note by taking this expression here, which is the pseudo-inverse of nabla G, right? So if we take, so this is u s plus to the minus 1 y transpose times nabla f of x star. This looks like a pseudo-inverse. Yeah? It is actually the pseudo-inverse of the matrix that we would get from y s plus and u transpose, and then the pseudo-inverse. So that's what this is. But this, as you see from just comparing it with the expression here, is the pseudo-inverse of nabla G. So we get the multipliers by a pseudo-inverse of our constraint Jacobian applied to the gradient. It's just something I found interesting. I wanted to share with you in case it might be useful at some point. Yeah, so it doesn't give a complete meaning to multipliers, but multipliers are having, they could be generated this way if you want. Okay, so that was everything that regards the optimality conditions. It's a summary, but now I want to become computational again. So what we do today is we want to see how we can use these conditions in chapter 12, which is on equality constraint optimization algorithms. So that's what we really want to do now. And as you might guess, and as I said already, the aim will be to solve this set of equations, yeah? Which we can write a bit shorter. So we are using the Lagrangian, we can actually write it like this. Actually, I don't put the star yet. The star will be reserved for the solution. So the aim is actually to solve this thing. And as we have already pointed out, this has the beautiful property that if you regard it as x in Rn, and lambda lives in the number of constraints, and then you see that this is also m conditions, and here we have n conditions because the gradient with respect to x. So it's really an n plus m by n plus m nonlinear equation system. So in principle it can be solved, and one can apply Newton's method for root finding. Yes? And of course we will not restrict ourselves to Newton, exact Newton, but we will use Newton type for root finding. Before we do that, actually, we will go into the case of a QP, because that will be beautiful and easy, and it's probably a good start. So we are now at 11, 12, 1. Or 2. I don't know how I got to 2 already. I think it will be 1 in the manuscript. And this is about equality constraint QP. Quadratic programming. And that means that we will now assume that our function, the objective function, is quadratic. So our objective function will be just G transpose times X plus 1/2 X transpose BX. Our optimization variable remains X. And then we have here a B plus AX equals B. That's our constraint. So we can use it also as an exercise to derive optimality conditions for it. So let's derive the optimality conditions once. Just to do this exercise, what is the Lagrangian for this optimization problem? It is actually gx and then plus 1/2 x transpose bx, and then minus lambda transpose b minus lambda transpose ax. What is the gradient of lambda, of L with respect to x? It is g. Here we have b times x. Here we have nothing because it doesn't depend on x. And here we have, we should just see it's the same as here, so we need to transpose that. So we get minus a transpose lambda. Please recall that the gradient must be a standing vector. So here we have the Lagrange gradient, and of course the equality constraints are here. So what will be the first order necessary conditions? They will be a collection of two equations, namely of this equation and of the equality constraints, and I write them already in this form where I put them a bit nicely spaced above each other. Bx minus a transpose times lambda. And here, and I collect also, so this whole thing should be equal to 0. That's what the first condition says, right? So the Lagrange gradient should be 0. And the second says that the constraint should be also equal to 0. So we have this set of equations, and if you look at it, you have here an x, and here an x, and here you have a lambda. And so I can write it equivalently, this whole thing that I have here in this box. I can also just write it as g b plus b a minus a transpose 0 times x and lambda being equal to 0, and then I have it in a form of a linear equation system. And because we like symmetric equations, and this looks nearly like a symmetric equation, we could just decide to have this minus sign there. So I move that from here to there, and it will not change anything. So then I look for minus lambda, and afterwards I need to put a minus sign if I have found the solution. So what we see here is that x and minus lambda can be given by the inverse of this matrix. With a minus sign in front applied to G and B, and we would have solved our QP. So it's extremely simple again, linear algebra and nothing else, and that is a beautiful thing. Of course, now the question is if this whole matrix here is invertible. It looks somehow strange. It has a 0 here. This was a Hessian. It was a symmetric matrix. Yeah, second derivative of something. Hopefully, this could be positive definite. A was the collection of constraints. Each row of this is one equality constraint. So we need to make some assumptions in order to assume that this thing is invertible. And there is a beautiful fact, and that is that these sufficient optimality conditions for the QP actually imply invertibility of this matrix. So let me just state SOSC for the QP. What will they be? They say if LICQ holds. What does LICQ mean for the QP? It means that the constraint gradients should be linearly independent, but the constraint gradients are actually the rows of the matrix A. Each row is one gradient. So LICQ is equivalent to saying that the rank of A is equal to M. That's the first thing. And what was the second thing? The second thing said second order sufficient conditions. Yeah, they said that the projection of our second derivative of the Lagrangian should be positive definite. But what is the second derivative of the Lagrangian? If you have this thing, then this is the first derivative, and you differentiate it again, g with respect to x, it's always the derivative with respect to x, then you get just b. So this is actually equivalent to saying z transpose b z is strictly positive definite. So these are the two essential things that we want to satisfy in order to be able to formulate the optimality conditions. We would say LICQ holds and the Hessian is positive definite. And if these two things hold, then it turns out that these first order conditions are actually well defined and can be uniquely solved. And this is what I want to express in a little lemma. And this little lemma I would like you to prove in question 3 of the current sheet. And this lemma says that we regard a matrix, namely just it's completely algebraic lemma, so to say. So we just look at this matrix, yeah, where B is symmetric. And that's it. And then it says if the rank, okay, and I should say the dimensions, of course, are the ones that we would assume here, namely what is always the dimension B is element in R n cross n, and A is element in R m cross n. So we have m constraints. If rank A is equal to m, and now we would say for all p that are in the null space of that, so we say it with AP equals 0, and we regard all the p's that are not 0. So then we have actually all the p's that are non-zero but in the null space, and for these vectors we want to have P transpose B P is strictly bigger than 0. That's actually the same statement as this one. So we just say for all those that are in the null space, the product of the vector with the Hessian should be strictly positive. That's actually second order sufficient. Yeah. If these two things hold, then the matrix, so we regard this matrix, and we call it, for reasons that I will explain in the next chapter, KKT matrix, which is actually following some people that proved the more general form of these optimality conditions, but then this KKT matrix is invertible. Yeah, so it's all about this matrix. And if this matrix is invertible, then actually we can solve this uniquely and we are happy, and the QP is done. Maybe there is a little thing just to state, because it's interesting to know about. We can also just look, like we did once for the unconstrained case, what is the optimal value of our QP at this point. Yeah? So we could also see what is actually the function, what is the value when I say minimizing G transpose X plus 1/2 X transpose B X subject to B plus AX equals 0. So this whole thing has a value, and there is a beautiful formula that is also relatively easy to derive by plugging into this solution into the objective function, and you get this interesting relation here with a minus 1/2 in front. So I will not do it, but I just wanted you to know that this minimum value itself is actually getting negative And it's getting more and more negative the bigger G and B are, so to say. No, this statement is not completely right, I should say. Depends really on the values, but this expression one can derive. If you want, we could do it. We just take the solution and plug this x value into the objective. Okay. So we have a system, a linear system that we would need to solve, but this linear system might be big, right? So this B, A transpose 0 matrix could have a large scale, so it would be important to think of how to factorize it and how to compute it in practice. And of course in MATLAB you could just use the backslash command, or you could just say factorize it, compute the inverse even, but it might be computationally not so efficient. So what I would like to discuss are a few methods how you could actually solve this linear system. And these methods have different names, and I would like you to know about these names. Okay? So this is how do we solve this linear system? And so the aim is actually somehow to factorize this matrix B, A transpose to solve the first order necessary conditions for the QP. So these would be the first order necessary conditions for the QP. And what I mentioned already, the first variant that you could use is what I call brute force. You would just say, this is just a matrix. I don't care that this matrix has all these zeros here, for example, and I don't care that it's a symmetric matrix, which are all interesting structures, right? But I could just say, let's disregard it and do, for example, an LU decomposition. You obtain by calling an algorithm that does a Gaussian elimination, LU decomposition. And you might even have a dense one of this matrix. So that would be one way. Do you know what is an LU decomposition? Everyone happy or not? No? So I just define it in brackets. So actually you can write any matrix that's invertible as L times U with L lower triangular. So it has all zeros here, and it has actually ones on the diagonal and something on the lower diagonal. And U will be an upper triangular matrix which has something here and there, but zeros on the lower diagonal. And also the U will have a non-zero entries. So then you can easily invert the L and the U. Actually, you will not invert them explicitly, but you will actually, when you solve now a question, a system of equations that says, let's say some residual plus M times some vector W should be equal to 0, then this is of course equivalent to saying R plus L times U times W is equal to 0. And now you will actually solve this system in two steps. So this R is actually given. You can first obtain, so you can actually obtain a Y. So you first say R plus L Y is equal to 0, and then afterwards the you have another equation which says y plus uw is equal to 0. And of course this is meaning y is equal to minus L to the minus 1r, and here w is equal to minus u to the minus 1y. Yeah? So this is basically what happens, but you will not, of course, not solve, compute this inverse, but you will actually do a back substitution, which you can easily see that if you, for example, have a system with this L, the first component you get just from the first equation, because there is nothing else than the 1 here. So you can easily get the first component, and then you have the second component, and so on. Triangular substitution is what we call that. I mean, this is the way you can solve every linear system, and it's reliably doing it. If you do pivoting and so on, everything can be very nice. But it's a bit brute force here, because we disregard the fact that we have this special structure. We just said, apply this algorithm that decomposes my matrix into L and U, and then goes on. There's a question.
Why it's not minus? The second angle, right?
There should be a minus. I thank you a lot, yeah. So this is with a minus sign. Thank you. Great. Mm-hmm. Because, yeah, we say actually that this UW is equal to Y. Yeah, absolutely. Yeah?
Yes.
That helps. Okay, makes everyone happy. Thank you. Great. I said already I call this a KKT matrix. Just accept that I call it this way. Yeah? We introduced the so-called KKT conditions a bit later, but in optimization this matrix is called KKT matrix. What you can also do is something which I don't want to go into detail, which is called an indefinite Cholesky. Factorization. And that is a decomposition which basically decomposes this matrix into something, so this matrix M is decomposed into an L and a diagonal and an L transpose, where the diagonal contains positive and negative entries. And L is a matrix like this L. So that's something that exists, and there are good routines for it. And I think one good routine for that is maybe my friends can help me. It's this Harwell HSL routine, HSL, and then it's which one? Which we usually like to use with IPOpt. Maybe Dimitris can help here. Sorry? I think it's MA27, right? So that is, I think, the one that is used a lot, but I'm not 100% sure if that's not for... Anyway, there are Harwell names for routines. Dimitris, the symmetric indefinite Cholesky. You don't know which one. Okay, sorry for this, so I'm not certain for what you should search. But anyway, you can get very elaborate, nice routines for that. But I want to go on. And I want to introduce a method that we can easily understand, and which is called the Schur complement method. And this method looks at the specific structure of our system. And if you think of the system, what that we want to solve is, this one. It has two unknowns. It has x and lambda. And we can also decide to to eliminate one of the two systems variables first. And if this B here turns out to be an invertible matrix, which it sometimes is, then we could just eliminate the x as a function of lambda, and then plug this x into the second equation and then solve the second equation. Then we get the lambda, and after we get the lambda, we can get the x from the lambda. Yeah. So this is applicable if B is invertible. So if this matrix B is invertible, usually positive definite, because we want this convexity, but then we actually eliminate x and we just say x is obtained from the first equation as being the inverse of B applied to, let's do it, A transpose lambda minus G. So that is an elimination that would then be possible, and then we can plug this into the second equation. And so if we plug this x into the second equation, then we get a system which actually says B plus A, B to the minus 1, A transpose lambda minus A, B to the minus 1, G equals 0. So I've just plugged it into this equation, and then I see that here again I have a symmetric matrix which lives now in the dimension of my constraints. So it's a quadratic matrix of the dimension m, where m was the dimension of my constraints, and I could eliminate it by just solving lambda being this inverse of that matrix, A B to the minus 1 A transpose to the minus 1, and then I have here A B to the minus 1 G minus B. So, of course, when we invert, again here we would use not a direct inversion, but some factorization. For symmetric matrices, one uses Cholesky, and the same here. So it would mean 2 Cholesky factorizations. And maybe someone wants me to explain Cholesky. Did you hear about Cholesky factorizations before? No? So it's maybe better to also explain what is Cholesky. So what is here? That was the LU. Yeah? And so what is a Cholesky decomposition? It's something which is applicable to symmetric to positive definite matrices, and then you can write B being L transpose, or actually, yeah, this L being something which has entries only on the lower diagonal of the lower triangle part of this matrix, but it has some possibly non-one entries here. And so the process of computing this factor L, which is a relatively nice and efficient algorithm, this process is called a Cholesky factorization. And then again, because you have L transpose, it's actually a special form of LU decomposition. Yeah, because this L transpose is, of course, an upper triangular matrix. And so you can apply the same algorithm here, but it turns out that this and this is the transposed matrix of each other. Okay, so that's all a lot of details which we don't need to care about. It's just that you know what people can do. But as I said, this whole method at all is only possible if B is invertible, and usually we even only like it if it's positive definite, because then we can use this very nice Cholesky algorithm. Yeah?
Did you write
This one?
This is also a Cholesky.
No, that's called an indefinite Cholesky, so it's something a bit more general. I should have introduced Cholesky before I introduced indefinite Cholesky. I think that would make more sense. Probably the best way would be that in the unconstrained part I would have introduced Cholesky, because that's where you could already use it. And today I could just build on that knowledge. But indefinite Cholesky is a way to factorize the whole matrix. This whole matrix, you can just say, is a symmetric matrix. And because it's a symmetric matrix, there exists a decomposition which is lower, diagonal, and upper. Yeah?
It's not exists originally.
No, the normal Cholesky, let's say, that only exists for positive definite matrices. Yeah? So indefinite Cholesky exists for all possible matrices, while Cholesky only for positive definite ones. Yeah?
And in the Cholesky case, it starts in the diagonal, and in the indefinite, it's once.
Yes, actually, no. It's in the indefinite one here could be positive and negative entries. The funny thing is, if it would be all positive ones, you could also take the square root and then bring them into these two matrices of all the positive entries, right? You see what I mean? And then you would actually have also a Cholesky decomposition. But at the moment, from the moment that there's one negative number here, you cannot distribute it to the left and to the right, at least not with real numbers. Yeah? Okay. More questions regarding the overview and the three methods presented until now. So I want to continue with a method which is, so to say, the alternative, the main alternative to this, what we call the Schur complement here, and that is what we call the null space method. I should say this is also called range space method sometimes. But I like Schur complement method better, but this one has a really nice relation to null space method. So it's the same idea as this one. We have two equations, but instead of first solving one of them, you solve the other first. Yeah? But this one it cannot directly be solved for x, and it doesn't depend on lambda. Yeah, because it was an underdetermined system for x, right? So this was restricting the freedom of x's in which we can move. But we know already that there was a basis for that, namely this Z matrix. Yeah, so you could obtain first a solution, a general solution. First, find general solution to this b plus ax equals 0. And that could be, for example, that you say x is equal to z times v, yeah, and z will be this null space basis, plus some value that I call y, with b plus ay equals 0. So that is what this y needs to satisfy. It should just be a special solution. So one solution. So one feasible point. The y is one feasible point, and z a null space basis. So there are many ways of how to compute a null space basis. But of course, we could use the SVD as we did before in our theorems. Yeah. But there is a slightly cheaper way. Get Z from SVD, or cheaper, could be obtained from a QR decomposition. It's another matrix decomposition of the matrix A transpose. And so now I think I should also explain what is a QR decomposition, right? So if you have a matrix, maybe I call it, I want not to call it A because I want to apply it to A transpose A. So B, C, D, E, say. So what is a QR decomposition? So we have a matrix E. This E can be written as Q times R with with Q orthonormal. And R has a special form which is given by something which is upper diagonal. This is this R matrix, and it has zeros everywhere else. And so this matrix Q can also be written as, and I will directly write it here as Y and Z times this R plus, so the positive part and the zero. So this thing I could also call R plus, with a lower plus and a zero. And it has a lot of similarity with this SVD, so please notice that there is also an orthonormal matrix here, and also something which is invertible, but actually the other factor, the one that's on the other side, this U thing, is not present here. So it's cheaper because we don't need it. And now the interesting thing is if we have A transpose, and I write it directly in this form, if A transpose is given as Y and Z times R plus and 0, and it's of course the same as Y times R plus. So the Z part is actually not needed, but the Z part has the property that if you have A times Z, then it's of course R plus transpose Y transpose Z, and it gives 0. So you see that Z is actually always, whenever you put Z, so to say, into the A, it will give 0. So Z spans the null space of A. So this is now applied. This was a general definition, and if I choose for E A transpose, and then I apply the QR decomposition, then I get from this QR decomposition the null space basis. And if I have this QR decomposition, I can also obtain a special solution from it. Let's see how we do it. So we have B plus AY, and that we can write as B plus A will now be R plus transpose Y transpose times Y, and this is a big Y and that's a small y. And we could just choose to find this vector together, which I call just maybe I call it Z. No, that's too confusing. I call it X, Y, Z. W. We didn't have that since a while. So I can get the W exactly as minus R plus to the minus transpose applied to B. And then I could actually choose to have Y to be the Y component times W, exactly, because that, if I have this W which I can compute uniquely, then I can multiply it with Y, and if I with a big Y, and if that gives me the small y, then here we have basically B plus R plus transpose Y transpose Y times W, and then this is a unit matrix, and I basically see that it will be 0. So I could use the QR decomposition for both things, for computing the Y and for computing the Z. And so now I have a way to find a Y and a Z, and then I have basically solved the linear constraint. So I can now write X equals Z times V plus Y, where Z and Y are given and already computed, and now I can reduce my whole optimization problem to the space of V variables alone, and I have an unconstrained optimization problem. Because I've eliminated the constraint, I can now plug in, there are different ways of dealing with it, but I think the easiest is actually to just plug it into the objective and then find the value of V. And afterwards we can use this equation to find the value of lambda, if we want it at all. But let me just first try to plug it into the unconstrained problem. So we get an unconstrained problem. And this problem will be minimizing over V. So in the remaining space, our objective, which will be G transpose, and then Z, V plus Y, plus 1/2. And here again we have Z times V plus Y. And that one multiplied with the objective, Z plus V, Z times V plus Y. And we can solve that by setting the gradient to 0, but then this one we need to first see where's the gradient actually. So this is, maybe I collect all the linear terms. It will be a bit nasty and a bit collecting a lot of terms, but I can actually directly differentiate it. So that's the function f of v, and I can compute the gradient with respect to my variable v of this whole thing. And I will get here a gradient, so it will be z transpose g from here. And then here I will have an outer and an inner derivative, and I will get a plus, and I think I directly I try to do it online, so to say. So we get here a z transpose b zv plus y. I think that's the correct expression. And we see that there's some term which is depending on the v. So z transpose g plus b y, so this is these terms, and then plus z transpose b z v, and that whole thing should be equal to 0, and then we can find the v. So we can get v as the negative of z transpose b z, and which is actually the reduced Hessian. And then apply to the residual that we had here. And I hope that this is also what I thought I had. Yes, it's at least the same thing I had in the script. So now we have a way to get the v. And so when we have the v, we have also the x. But again, we need to have one inverse here. After we have the v, we now can try to compute the lambda, and let us try to do it. How do we get lambda? And we have now the x, so we can actually use this equation system in order to find lambda. So we have the gradient g plus bx, so we get v and x. So that's clear how we got them, but now we need to get lambda back. And so I can plug in the right solution that I computed and then have here minus a transpose lambda, and that should be equal to 0. So I need to find a lambda that makes this whole thing possible. And because this seems to be an overdetermined system of equations. This is not a square system, but I can use my QR decomposition again. So I have actually g, let me just say it's actually a transpose lambda equals g plus bx, and bx is now fixed, but this a transpose lambda can be also written as this whole thing, right? So it will be y times r plus equals g plus Bx. And what we will now do is actually we multiply this whole system with y transpose, and then we get an equation that the lambda needs to satisfy, and that uniquely satisfies, determines lambda. So actually we will have lambda equal, so if we multiply this with a y transpose, this will be a unit matrix, and so we will get r to the plus to the minus 1, here with a y transpose times g plus bx. And the interesting thing is if we multiply this whole thing with a z, we will somehow magically get 0 on this side, because the gradient, exactly, that is the gradient of the objective at the solution, and that is multiplied with z 0. So it's an overdetermined system, but it can be solved with this approach. So at the end we get the lambda from, again, something we can easily compute. This thing is computable, and then we invert this R matrix in order to get the lambdas, if we want. So now we have the other big family, so that took much more time. So you see the sure complement method was much easier to write down. That's why sometimes people like it also more. It's easier to write down and also sometimes to implement. But it depends on this matrix B being invertible, which is not related to our sufficient optimality conditions, right? The null space method is applicable directly if you have LICQ, then this QR decomposition will result in a matrix where this R has a full rank, because LICQ means that this matrix has actually, which is decomposable like this, has a full linearly independent columns here as well. So the null space method is always applicable if we have LICQ and second order sufficient conditions hold. So that's one nice feature of this method. So it's more generic, I would say. Then there are two things that I still want to mention, and one is that you could also use sparse direct factorizations. I think this is a bit nearly the same as what I said with indefinite Cholesky. Sparse direct factorizations. Yeah, I think I should merge it with point 2, because that also can be such a thing. And then the last one, you could also solve the system iteratively, and I will not go into detail. So you could also try to do some iterative refinement techniques on the linear system that I have here. Like GMRS is one method that could be done here. There are many others. So this is not that we all should become experts in linear algebra, but we should be aware of the fact that at the end we need to solve all these linear systems at some point, and at least we need to know how to use these routines and maybe how they are called. Yeah? And that's why I mentioned a few names that I would like you to not get completely confused when you find them in the literature or in the manual of a book, yeah? or a manual of a solver. Okay, so to summarize what we did in this hour before we do the break, I just wanted to say solving an equality constraint QP, this one, amounts to solving a linear system of equation, namely this one, and because this matrix has a special structure with these A and A transpose and the B and the symmetry, this system can be solved in a structure exploiting way, and this first one, the brute force method, would not be as efficient as, for example, the sure complement method or the null space method, which explicitly use the structure that we have. So these would be more efficient, and if you can apply them, one should apply them. Yeah? If you are lazy and you are just in a small scale example, you can also do the brute force approach. And that's what you can also do in the exercise sheet that we do now. Yeah? Just use the backslash operator in MATLAB and you are done. Okay, we will have a 10-minute break and we continue, I would say 15 past. Let's continue 15 past and then stop quicker. Okay, let's continue. And we have looked at one linear system, which comes from a QP, but which actually is only a linear system so far. And I want to generalize the Newton type optimization methods to equality constraints now. And this is what we do in section 12.2. Call it the Newton-Lagrange method. Because it's based on the Lagrange optimality conditions and the Newton method. So what we had, and you remember that, we had this system of equations that says that the Lagrangian gradient should be 0 and that the constraint function should be 0 as well. And the aim is actually now to find the root of this system. So for this system we want to find a root, and in order to do so we will actually just apply Newton's method. And how do we apply it? We just define our residual vector and our variable vector so that it comprises all the variables. So here we have x and lambda together in one vector that I will call w, and I will define a function f of w which will just consist of these two residuals, which then actually I can write it like this: nabla f of x minus nabla g of x times lambda, and then g of x. And this is a function of x and of lambda alone, so it's actually a function of w. And this root finding problem I can now solve. What does Newton's method do? You remember what Newton's method does. It just linearizes the system at a current guess. So we use Newton for f of w equals 0. So that's what we want to find. And that means we need to start at a guess. W0, which will be consisting of an x0 and a lambda 0. And then we can linearize this equation. And then we get actually the wk plus 1 from this typical relation that we have in Newton's method, which takes the derivative of our nonlinear function, inverts this, and applies it to the residual. So we have the second derivative of this big function f. Not the second derivative, but it will be the first derivative, but because it contains already first derivatives of our problem functions, it will actually involve second derivatives. And this matrix, or this system I want to look at. And I want to write the equivalent system because it's a bit easier and not involving the inverse. I will just write the system which we have is actually f wk plus this matrix times wk plus 1 minus wk. This whole thing should be equal to 0. Right? So that's a complete equivalent statement of this equation. But this is what we can write, and I will omit this to make, so to say, to save an index, and also to make sure that this is, so to say, the unknown of our linear system. This is a linear system now. So what is this linear system? It will be First, of course, the gradient of our Lagrangian, and then the residual of G. So that's the first part of our linear system. It's just a re-evaluation of these two conditions at the current point. And then we have here something which is now the derivative of the first thing with respect to x. And then we need the derivative of the first with respect to lambda. So here we will have now multiplied with x minus xk and lambda minus lambda k, and then this whole thing should be equal to 0. So that's what I want to have, and so I need to state this derivative here, and this derivative with respect, so it will have 4 blocks, and here's the first block. It's the derivative of the Lagrange gradient with respect to x, and I will write it, because it's short, like this. So it's the second derivative of our Lagrangian. What do I have here if I differentiate that with respect to x? I will have the transposed gradient, right? So that is my Jacobian of the constraints. If I differentiate the first equation with respect to lambda, which is this block here, then I could either differentiate that with respect to lambda, but it actually helps to look into this form, and I see that lambda enters linearly, so it's minus nabla g, without a transpose here. So here I have minus nabla g. Yeah, it's more consistent if I drop the argument, because it's always xk here. And of course, the last equation, this one does not depend on lambda, so I get a 0 here. And we see this looks quite familiar. It looks like the thing that we had. We just can make it more beautiful by making a bracket around this and putting a minus sign here and then removing the minus sign here. So then we have exactly the same symmetry as before. And please keep in mind that the functions are all evaluated at xk and lambda k. So all these things are evaluated at the current iteration. So this is a linear system that we want to solve. And now the question is, when would this be invertible actually? And the beautiful thing is, again, we had already this lemma that you will prove in the exercise sheet, that this matrix is invertible if that matrix is positive definite on the null space of that matrix. Yeah? So invertible, so this whole matrix, big M is invertible if this thing is positive definite on the null space of the nabla G transpose of the constraint Jacobian. And this was exactly, this is not the only thing, and of course we also need that nabla G has the rank of this, rank of nabla G is equal to M. That means it has full rank. So all the columns of nabla G or the rows of the transposed version are linearly independent of each other. So then it is invertible, and this is just exactly what would be LICQ and sufficient second order sufficient conditions. And we expect actually when we are close to a solution which satisfies these things, then if we are at the solution itself, then this matrix will, and if we are at a solution which satisfies LICQ and second order sufficient conditions, then this matrix will be invertible at the solution. And when we perturb it a little bit, so when we evaluate this matrix in the neighborhood of a solution, it will still be an invertible method. So that means Newton's method is well defined. Newton is well defined in a neighborhood of a nice we call it actually a regular solution. So if we have a regular solution lambda x star and lambda star with LICQ and second order sufficient conditions. So that would be a regular solution, a nice solution which has all the things that we'd like to assume. And in this neighborhood actually this matrix will be similar to the one that we have at the solution. And because it's invertible at the solution, it will be invertible at least in some neighborhood around the solution. So that is a nice effect already. And in principle, we can write down our method now. And what would be the method? It would just do Newton's method. It iterates. It starts at some point. It performs this iteration, and it stops if the residual is small enough. That would be the method. And if you are lucky, it will converge. If you are not lucky, it will diverge, or it will converge to a non-optimal point. But that is Newton's method. Okay. This method can be a bit more interpreted more interestingly, and I want to actually give you one different point of view of this method in terms of, because it looks like the same linear system that we saw for solving a QP. And you remember for the normal Newton's method for unconstrained optimization, we had this quadratic model interpretation, and so the same thing we can also do here. And this one I want to give you. But before I can do it, I want to introduce something which is a slight modification of this system. So I will actually introduce lambda. I will modify this a little bit by using the following equality. I have maybe I should actually write it a bit more in detail. So sorry. So this is the Lagrange gradient at the current iterate is given by the gradient of the objective at the current iterate times the gradient of G at the current iterate times lambda k. Right? So that is just the definition, and that is the thing that is at the top left corner of our linear system. But because this times lambda k appears again in the right corner, and it appears with a minus sign, I can also leave it away, and then these two things cancel, and then I can say actually that the above system is equivalent to saying f at xk. I omit the other part for a moment. Here I have the same second derivative, but here I have now nabla g xk, the same thing that I had before. But in my vector of unknowns at the bottom, I don't have this. I have only minus lambda, and the other part is now cancelled. And here I still have x minus xk. So I have now the same matrix, but I have a different vector here. Namely, I have the gradient vector here, and not the gradient of the gradient of the objective, but not the gradient of the Lagrangian. And the price, so to say, I had to pay to make this a bit simpler, because it's now only depending on x and not on lambda anymore, right? The price I had to pay was to accept that I compute the next multiplier directly, and I don't compute a step in the multipliers. So this is an equivalent system of equations, and I can, if you want to compare it with the QPs that we had before, I can actually state a QP which has this as the optimality conditions, right? Because this looks like optimality conditions of a QP, like we had written it before. So I could also say that this is equivalent to first order necessary conditions of a QP. And which QP is it? It's actually a QP which says that I want to minimize over all x in Rn an objective function which is the gradient plus a quadratic term which depends on the distance x minus xk, and in the middle I have the second derivative of my Lagrangian. Yeah. And I have constraints, and what are the constraints in my QP? It is actually g of xk. This constraint, that was the residual of the constraint, and that was the constraint matrix, plus nabla g of xk transpose times x minus xk equals 0. So is this QP something you accept, that if I would now take the theory that we applied before to this QP, I could compute the Lagrangian, I could compute its optimality conditions, and then I would actually arrive at these conditions here. So the QP solution will give me an x QP and a lambda QP, which are actually the solutions of the linear system. So they solve the Newton system. It's just a different viewpoint. I mean, in order to solve this QP, you would have to solve this linear system anyway, right? So it's just a different viewpoint, and computationally it doesn't change anything. You would just solve this system with the methods that we discussed before. But I want you to understand that it's actually a linearized version of our optimization problem. When you look at it, it's really, this is the first order Taylor series of our constraint. So that's like Newton's philosophy, linearize your things and then solve something which is linear. But here we have an expansion of our objective function which contains a second order term which does not actually involve only the derivative of the objective but also of the constraints. And this is important. So it will necessarily needs to be the second derivative of the Lagrangian here in order to make sense in order to get quadratic convergence. So this is what we call the quadratic model interpretation. Okay, I think I want to still introduce you to some variant of these technologies, but I think I want to do it a bit different than it's in the current script. And I will just remind you that in the case of unconstrained optimization, we were allowed to replace the Hessian with something that is just an approximation of the Hessian and still get possibly not quadratic, but still get convergence to an optimal point. And the same thing is also possible in equality constraint optimization. So in more general, what we can do, we can replace this second derivative of the Lagrangian by a matrix BK. And I don't specify yet what this BK is, where BK should be similar but not necessarily equal to the second derivative of the Lagrangian. And there are many ways to do it, and one way that I want to start with is the constraint or generalized Gauss-Newton method, because it's a method that is very nice to use and very widely used and very successful. So let me just continue with, I think, 12.4, what we call the generalized Gauss-Newton method. And this generalized Gauss-Newton method is one way to solve optimization problems which have a special objective, namely a least squares objective, but with constraints. Yeah, so this it's actually applicable if our objective function is given as the squared residuals of a nonlinear function. And that means actually that our optimization problem has this objective but still some constraints. Yeah? So we actually have this. Yeah? Usually I don't like this notation where you define something in the minimization, but here just accept it. So we minimize an f, but this f has this special form. So what the generalized Gauss-Newton method does, GGN, you just call it GGN. Sometimes it's also called constrained Gauss-Newton, but I think generalized Gauss-Newton is more often used, so I will correct that also in the current script. What this method does, it will actually solve in each iteration a linear quadratic version of the original problem. And you remember what the original Newton method did? Do you remember the normal Newton's method? It would just say I evaluate my nonlinear function f and its derivative. So this is a big f, but it's a different f than this one. Yeah? It's just another function which has lots of residuals. But this would be the first order Taylor series. And I just, you remember maybe that the normal Newton's method would just linearize the objective under the least squares term, and then we use the pseudo-inverse to compute the next step and so on. But here we have also constraints. So we just say, let's keep also the constraints, but also in a linearized form. Equals 0. And you see here, by the way, that my way of using Jacobians and gradients, is redundant. I could also have here nabla f transpose, right? So both would be. So here I use both conventions in the same problem, which is a bit funny. So if you do this, what you need in order to define this problem, you will actually get xk into your problem formulation, and what you get out is an xk plus 1. Or the solution of this QP. And the way to solve this QP, we know we can do it by looking at the optimality conditions of this QP, which we will do at the next hour, I think. The constrained Gauss-Newton or the generalized Gauss-Newton method is too important to just treat it at the end of this lecture. I want to start next time with explaining and analyzing this method. And because we did a short break, we can also stop a bit earlier today. Okay, I stop in the middle of the Gauss-Newton method, but it would take more than 5 minutes to explain it well. And I want to rather summarize what we did now in the second hour. Is we basically wanted to solve a nonlinear root finding problem. When we linearized it, we realized that there is a very special structure in this linear systems, which is exactly the same structure that we had observed for QPs. So we can actually say the Newton's method is nothing else than an iterative solution of QPs. And this inspired us then to say, okay, then if we have something which is already having this Gauss-Newton structure, then we could also have the same idea as Gauss-Newton, namely linearizing everything that is nonlinear and then having something simpler, namely in this case a linear problem or a quadratic equality constraint quadratic problem. And that one we can solve easily actually, again with the same linear algebra, and we will have a look at the convergence properties of this, and of course they will depend on the similarity of what Hessian is implicitly assumed in that method compared to the exact Hessian of our optimization problem. Are there questions think I had the feeling today I was a bit too speedy. Is that correct? No? It's okay? Smile, half smile. Okay. I think the sheet will be rather easy. So in that sense, I think even if this was fast for some, then it might still be good because the sheet is easy and the week is hopefully in equilibrium. So we will see next Tuesday and continue with equality constraint optimization algorithms. Thank you.